Welcome to this explainer. I am absolutely thrilled you're tuning in today because we have a fantastic goal ahead of us. We are finally going to conquer those painfully slow Python scripts once and for all. Seriously, if you have ever written a script to, say, download files or scrape some web data and felt like you had enough time to go brew an entire pot of coffee before it even finished, well, you are in the exact right place. Let me ask you a quick question. Have you ever just stared blankly at your terminal, watching that little cursor blink, waiting for a massive batch of files to finish downloading? Or maybe you've built a web scraper that pulls data from 100 different pages, and it's just creeping along at an absolute snail's pace. It's incredibly frustrating, right? But why exactly does this happen? Well, to understand the solution, we first have to really understand the core problem.
Okay, let's dive right into this. Here's the fundamental contrast. On one hand, you have your modern, lightning-fast CPU, which is capable of billions of operations a second. But on the other hand, you have a sluggish network response. Tasks like web scraping or downloading files are what we call I/O bound. This basically means the speed of your program isn't limited by how fast your computer can think, but by how long it literally has to wait for input and output operations. It's like waiting for a web server on the complete other side of the country to reply. Meanwhile, your super fast CPU is basically just sitting there idle, twiddling its thumbs.
Section 1, multi-threading and the Python blind spot. Let's get into it. So how do we fix this idle wait time? The logical first attempt for a lot of developers is to say, hey, if my script is just waiting around, why not run multiple tasks at the exact same time using multi-threading? And honestly, it sounds like the perfect fix, but Python has this very specific architectural quirk called the global interpreter lock, or the GIL. The GIL is essentially a massive bottleneck. It's a mutex that fundamentally limits standard Python, specifically CPython, to allowing only one single thread to use the Python interpreter at a time. Why on earth would it do that? Well, because it protects the reference count that is managed for each object from garbage collection. Without the GIL, multiple threads trying to update an object's reference count simultaneously could completely corrupt your data. But the huge downside here is that it prevents true parallel execution of user threads. Now look, that doesn't mean threads are completely useless in Python. Multi-threading is actually still pretty great for I/O-bound tasks, because a thread will temporarily release the GIL while it's waiting for a network response, which lets another thread run. But here's the catch. When you introduce threads, you introduce a high risk of race conditions. This is where threads might try to modify the exact same shared data at the exact same time, which corrupts it. And fixing that, well, it requires implementing complex lock and synchronized queue structures. Honestly, it just gets really messy really fast. Which brings us to Section 2, multiprocessing. Basically, brute force concurrency. Now, what's really interesting about this is the thought process. If threads are locked to a single process, why not just create entirely new, separate Python processes? Well, because of the sheer amount of heavy lifting required. Because each process is totally independent, yes, it completely bypasses the GIL. Fantastic. But look at the cost here. For every single new process, the operating system has to create a brand new process control block. It has to allocate completely separate memory spaces just to avoid that data corruption we talked about. And if you actually want those processes to talk to each other, you have to establish complex inter-process communication using tools like pipes or specialized queues. It just eats up your system memory rapidly. All right, Section 3, enter asynchronous programming, the real game changer. So, multi-threading gives us the GIL and race conditions, and multiprocessing is a massive memory hog. There has to be a better way for our slow web scrapers, right? Well, yes, there is. Let's walk through this concurrency showdown to see how asynchronous programming builds into a complete picture. It neatly categorizes everything we've been discussing. Multithreading is good for I/O, but it's GIL constrained. Multiprocessing escapes the GIL entirely and is great for CPU-heavy tasks, but it uses separate memory. Now look at that bottom row, asynchronous programming. It is ideal for I/O-bound tasks. Is it GIL constrained? Technically, yes, because it runs on a single thread in a single process, but here's the kicker. The GIL is entirely irrelevant here. How on earth does a single thread handle multiple things at once? Through a brilliant concept called cooperative multitasking. Here is the absolute key definition you need to remember. Cooperative multitasking is a style of execution where your code voluntarily releases control whenever it hits an idle period or a wait time. So instead of the operating system forcefully switching between threads or processes behind the scenes, your asynchronous Python script literally hands control back to a central manager the exact millisecond it realizes it has to wait for a network delay. And this brilliantly illustrates the whole concept. Think of the event loop, which is the core manager of asynchronous Python, like a highly efficient chef in a kitchen. The synchronous chef puts a pot of water on the stove and just stands there, literally staring at it for 10 minutes until it boils, doing absolutely nothing else. That's your standard Python script waiting for a web page to load. The asynchronous chef, however, puts the water on the stove, realizes there's going to be a wait time, and immediately pivots to chopping vegetables. When the water finally boils, they just go right back to the pot. They get vastly more done in the exact same amount of time, all using only one chef. So, under the hood, how does this actually work? Well, it relies on what we call the event loop. When you run an async program, the event loop registers your task. When that task hits an I/O delay, let's say it requests a file from Google Drive, instead of freezing the whole program, the task yields control right back to the event loop. The event loop then looks around and says, great, while we wait for that file, what else can I run? And it starts other tasks. Once that original file finally finishes downloading, the event loop just resumes the first task. It's an incredibly elegant juggling act. To actually build these asynchronous scripts, Python gives us the asynchronous module. It's pretty straightforward once you get the hang of it. You'll define your functions as coroutines using the async def syntax. To run them concurrently, you wrap them in tasks using asynchrono.create_task2. If you have a whole list of things you need to wait for, you just use asynchrono.gather. And to distribute workloads nicely, you can use asynchrono.queue. And the best part? Because this is all happening on just a single thread, you generally don't even have to worry about those data-corrupting race conditions that totally plague multithreading. Moving to section 4, let's look at a highly practical case study, Google Drive downloads. Okay, theory is great and all, but let's actually put this to the ultimate test with a real-world application. Here is the exact setup. We have a shared Google Drive directory containing 10 files. These files range in size from about 500 kilobytes to 3 megabytes. Our goal is simple. Write a Python script to download all 10 of these files to our local machine as quickly as humanly possible. If we run this synchronously, which is, this standard way most beginners start writing Python using a basic for loop, downloading one file, waiting for it to finish, and then moving to the very next one, it takes approximately 20 seconds. Just think about that for a second. For almost the entirety of those 20 seconds, your very expensive CPU is doing absolutely nothing. It's just sitting idle, waiting on Google's servers to send data over the network. Now, to unlock the true speed of async I/O, we have to change our toolkit. Standard synchronous setups use libraries like the super popular request module, but requests will completely block the whole thread. To get the actual benefits of the event loop, we must use specialized, awaitable third-party libraries. In our async setup, we swap over to AIO HTTP to make non-blocking network requests, and we use AIO files to save the data without blocking the system while it's writing to the hard drive. And the performance improvements, they honestly just speak for themselves. Our standard synchronous loop took 20 seconds, but by implementing the Async I/O module and running just 5 cooperative tasks in parallel, the download time completely plummeted to 4 seconds. And when we scaled that script up to run 10 tasks in the event loop concurrently, the total time dropped to a staggering 2 seconds. So, the absolutely crucial point here is 2 seconds. By simply changing the architecture of the script to use cooperative multitasking, we literally slashed the wait time by 10-fold. 10 files downloaded in just 2 seconds, all using a single thread. This right here proves the incredible, undeniable power of the event loop when you're dealing with I/O-bound tasks. And just to firmly validate this, the book Python for Geeks specifically notes, this is a significant improvement compared to the numbers we observed for the multi-threading and multi-processing case studies. When you are in the context of heavy I/O tasks, like web scraping or API downloads, asynchronous programming is undeniably the king. Mastering these concepts, as emphasized in classic texts like learning Python, is a massive stepping stone to elevating your entire programming toolkit. Concurrency isn't just some neat party trick. It's a foundational computer science concept. It's the kind of thing that transforms you from someone who writes scripts that just work into someone who writes highly scalable, professional-grade software. I want to leave you with this provocative thought to wrap up. Go look at your own code bases. Go find that web scraper, that API fetcher, or that data pipeline you built. It is highly, highly likely your script is spending 90% of its runtime just waiting around. Now that you truly understand the asynchronous event loop, what are you going to teach your script to do next while it waits? Thank you so much for joining me in this explainer. Now get out there and go write some lightning fast code.